Okay, you can see the expression on my face just before the camera died, so you don't need to see that. Let's go ahead and let me auto lock here. All right, let's talk about these really quick. I'm going to kind of go over the answers here. You've got a function defined here. It's a rational function. When it asks for f of 9, that 9 just goes right into where the x's are, and we just evaluate, no big deal. Now, when you do the x minus 1, however, the x minus 1 goes into the location where the x is. So it just kind of opens up like a window, and you can see it right here. In fact, what I'll do is I'll kind of write it in. This is the x minus 1 right there. And then we can actually simplify that a little bit. So it does change, okay, like here then, you can distribute the 2 and then you can combine what you have. So there are some changes that can happen when you don't just put in a number, but you'll just put in an algebraic expression. Okay, let me get this page here. All right. Okay, so we've got another one here. You've got g, the g of x defined here, and that 2 minus x, or 2x minus 1 goes right into the x location. Okay, so you can see 3 times the input minus the input squared. Okay, same thing. Just execute that carefully. Make sure you FOIL that out. Okay, and then distribute the negative sign to each one and combine like terms. This guy, negative 3x, okay, goes into each of those locations. Square that out. You will get a positive 9x squared, but you are subtracting that positive 9x squared. So this guy, you can just rotate the terms there, put them in any order you wish. Okay, here we have a piecewise function where we've got two very different functions here that's the word if, so we normally just kind of put a comma there. And this is for x is less than negative 3, this is greater than or equal to. So what we're looking for here is where do we plug in the functions. If you have negative 7 and you wanted to, let me minimize this here. You have negative 7, you need to figure out which of these two, which of the pieces you need to plug that in. Negative 7 fits into this domain here at less than negative 3, so he will go into this one. That is why it is here. Plug it in and just evaluate. Negative 3 actually belongs in the other one because that's where the bar is, and so he will go into the lower piece, this piece right here, the cubic, and you just got to carefully put him in, and it's no problem to just use your calculator. Okay, so these guys here, for each family below, you would just sketch the shape. This is our linear function, absolute value, quadratic, cubic looks like this, square root, cube root, reciprocal, greatest integer is always like a step, sometimes called the step function, sometimes even called the floor function. All right, that's it for the first page. We're going to move right along here, actually. You can pause this for any time that you feel like you need to. Okay, so paying attention to this guy, if the quadratic function is reflected on the y-axis, then you know that you've got to put a negative x in there. It's vertically compressed by a factor of 1/2. If it's vertical, that's the easiest one, then you know it's on the outside of the function. And yeah, that's it. Looks like we just have a quadratic parent. There he is, no problem. This guy is a cubic root parent, so we would put the cube root as the focus of the whole thing. We do know it's horizontally stretched, so that means the horizontal will be close to the x. And by close to the x, if there is a movement to the right or left, then that needs to be in parentheses. Even with the like you can't just put the 1/4 next to the x. The x minus 5, because we're moving to the right 5, that has to be in parentheses, and the 1/4 gets multiplied to those parentheses. That's very important for that to actually work, because you're also taking a quarter of the horizontal movement here. So you're not going to move over 5, really. You're going to move over 5, then stretch it horizontally. Okay. All right. Anyways, we're also going to move up 3, so it's going to be outside the parent function. Absolute value function says we get a maximum negative 2,7. So there's our negative 2,7. Okay. But then it also has a transformation applied such that it creates an absolute value. Okay, so you could have just left it at that. You could have put negative here. You could have put any negative in front here, just as long as it's negative to produce a maximum, but you could have had -2, -3, and -4. That's totally fine. Okay. All right, a certain function is vertically stretched by a factor of 2, horizontally compressed by a factor 1/4, and translated down 6. The new function represented is this. Okay, write the equation of the original function. Now that just seems unfair, because, okay, because we've got to work ourselves backwards. So this means then that if it looked like this, okay, to horizontally compress by a factor of 1/4 means that we need to have multiplied something by 4 here to get this on the inside, okay? All right, so a certain function, we're definitely going to keep, this is a greatest integer function, so we're going to keep that formation. And then it said that it was vertically stretched by a factor of 2. So having both happen at the same time is very rare, but you can see here that this means that whatever number was here was multiplied by 2. Okay, so this number was multiplied by 2, but horizontally he was multiplied by 4. And then it translated down 6. Okay, so this is what happened. So in order to get to go down 6, he needed to be up 4. So that if we dropped him 6, he would go to the x-axis. If he went down 4, then he needs to drop 2 more. Okay, so pretty tricky. All right. Okay, you guys did pretty well on the quiz with this, so not too worried about this. You can just kind of pause and take a look at it. Okay, it's pretty self-explanatory, I think. Next, this guy right here. This was pretty good, actually. You guys did a really good job with these. Just a few errors here and there, but there were no major point issues going on. So we've got a x rational function here that we started 0, 0. I'm going to put that dot right there. And 0, 0 means that we're going to move over to the right 4, down 1. So 1, 2, 3, 4, then down 1. This is our new kind of origin here. One thing I did notice, though, is I did notice that sometimes you guys would have your rational functions cross over the asymptote, and that can't happen. They have to be kind of pressured inside these windows, okay? And then also the 3 meant that we had to multiply 1 times 3 and 3 times 1. That's going to give us sometimes call it a k value. Okay, and then it looked like this right here was like a 2 times 1.5 and a 2 times 1.5. Okay. All right, so what else? You got to have it on this side. So you can have your domain is all real numbers except you can't have 4. All real numbers except you can't have -1 because for the range, because going straight across you're good until here. You'll never get that value because you'd be dividing by 0. Okay, but it's all good as soon as you get on the other side of 4. And then for the range, it's up to -1. Then you got to get on the other side of it in order to go up. Okay, there's a couple ways you can write this. This is kind of the fastest way. X-intercept is here. You guys didn't have too much of a problem there. Y-intercept, though, you might have to use the graphing calculator to get that. Okay, or you can just estimate based on what you see here. I just basically did it off your estimates. If you can do it without the graphing calculator, it's faster. It's probably just all in all easier. The extrema here is there are none because it shoots off to infinity in both directions. Increasing interval, actually this particular rational function is decreasing everywhere except where the asymptote is. So you could have actually just said something like this, okay? And then this guy's going off to -1. So this is very similar to the quiz. You guys went to, I think, +1 in your quiz. This guy goes to -1. So that's totally, a lot of you guys did really well in that. So congratulations. Okay, here's a quadratic. Moving over to 3, drop 4. And then we're going over 1, up 2, over 1, up 2. And that's because of that guy right there. Okay, so he's going up. So therefore our domain is all real numbers. Looks like we're all the y greater than -4, or you could have just went like this, -4 to infinity. I think that's a lot easier. X-intercepts, you had to kind of estimate there. That's totally fine for this. And here the y-intercept is when x equals 0, so we could have just plugged in a 0 right there, and we could have figured out what that is. If you wanted the x-intercepts, you could have plugged in a 0 for f of x, and then move the 4 over, divide by 2, take the square root, then add 3. That's where these numbers are coming from. Increasing, this guy is increasing from here in this direction, and then it's decreasing from all the way to the left to here, and then it switches. So it decreases coming this way, and then starts to increase going this direction. These guys shoot off both to positive infinity. Stop there. Okay, it looks like my camera is actually working again. All right, cool. Hopefully it doesn't tank out. Doesn't matter. It doesn't seem to affect the video. Okay, here we have a cube root. We move this guy over 4 to the left, up 3, so there he is. Okay, but then what happened was we got a 2 here. So the cube root has his anchor points right here and here. Okay, but because of the 2, we're going to move up. Now this is kind of like your new origin. So we're going to move over 1, but we're going to double that output over here, and we're going to go down double that output. So if you focus on the anchor points, these numbers, which are usually the hardest numbers to deal with, if you focus on the anchor points, they'll tell you kind of how to move from the core of the original graph. And it's usually right there at the origin, 0, 0. These guys play real nice. Their domain and range is beautiful. This right here, the x-intercept, you would have to estimate, okay? Or you could have solved for this by plugging in 0 here, and then subtract 3, divide by 2, raise it to the 3rd power, and then subtract 4. You're doing the opposite direction. You're doing the inverse in order to solve for this guy. There's no extrema because they both shoot off to infinities. This one's positive to the right, negative to the left, increasing the whole way, so all real numbers, decreasing nowhere. Okay. Hopefully I'm not going too slow, but you know. Okay, again, you don't even have to listen to me. You could just pause for the answer and just scrub. I'm just gonna explain it if you need to. These guys are crazy hodgepodge of functions here. We don't even care like what the equations are, although maybe we could figure them out. We don't have to. We're just looking here, domain here, 1, 2, x cannot equal, that one is actually filled in, so you can actually have positive 2. That's why he's not listed there. But you do have jump discontinuity there, and you have infinite discontinuity there at that asymptote, so we got jump, jump, infinite. Now that's jump, but you can see that it's filled in, and that's why it's still part of your domain. Okay, over here, you got the domain, all of these guys. As soon as it does a jump, it is filled in, so that's good. That means that you can have a closed domain. Everything's safe. Even though there's jump discontinuity, you can at least seal up the domain like that, so that there's no holes. This guy, everything less than 6, if this would have been filled in, we would have put a bar there, but there is nothing that is higher than this value. But this is implied that this is going off to infinity, even though I don't see an arrow. Okay, those arrows actually have to be there. So if we just put that there, then we might have said that this goes all the way down to 1, 2, 3, 4, 5, 6, 7, 8. You might have just put from 6 to -8. Okay. All right. Love these piecewise functions. I don't know why I think they're so cool. But let's see. We've got a -4 break, and we have a +1 break. We've got 3 different functions. One's a line, absolute value, square root. Here's our line that we drew. It looks like it connected to -6, and then it went down 3 over 2, down 3 over 2. So that guy was here, but then they erased the rest of it. This is just a negative absolute value, so he's just a V shape, but he's pointing downward. Looks like my face froze. And so who knows how long that was frozen. I have not been looking up. And then this guy here is a square root. He went over 1 and then up 3, and he's just 1, 1, and then 4, 2. So good. That's perfect. And that's it. Domain all real numbers. It's all closed in. Everything is bigger than -4, and it looks like we got 2 jump discontinuities. It's pretty much guaranteed that you'll have jumps there, but every once in a while they are connected. Okay, so here we are with the average rate of change. Remember, the average rate of change is just the slope formula, so don't overthink average rate of change. I'm not sure, and it's not really your class, but Algebra 2, just average rate of change, like slope. It's just slope. They think that they're two different things, and I don't know. But you'll notice that the difference here, though, is it's kind of understanding what the slope formula is doing. This -3 and that 2 are not coordinates. They are actually the two locations. Here is your B, that is your A. This is your f of B, and that is your f of A. So this is really f of B minus f of A, and all over B minus A. This is your, I'm sorry, that is your A, that is your B. Okay, so just do it again, and you should just work out the slope formula. Don't worry about that fraction. Okay, don't worry about a fraction getting here. Okay, you can use your calculator. It's not that, it's not, you know, don't let it sweat you. Okay, 5s will cancel out here for 1/2. All right, trying to go fast here. Okay, so it looks like this is actually the average rate of change here, except they gave you a formula, and it looks like they just want to know, like, okay, here's the formula, the model for the football. Okay, they want the average rate of change when it reaches its maximum height until it reaches the ground. Okay, so where does it reach its maximum height? Well, this is, the maximum height is actually -b over 2a, that formula right there, okay? And we take the -b, which in this case is 80, -80, divided by 2 times a. Okay, now that's 2.5. Now let's plug in 2.5, because that's actually when, after how many seconds it hits, okay? Then, until it hits its maximum. And how high are you? Well, take the 2.5 that you get here, plug it in, and you'll get 100. Okay, so now when you start at the max to the ground, well, how long did it take to reach the ground? Well, if your max is 2.5, double that. If your max is 2.5, then it took 5 seconds for you to reach the ground using the symmetry of the quadratic. And so remember, we spent the day working on these types of these problems with quadratics for max and min problems. And it looks like now our interval is from here to here. So from 2.5 to 5. So we needed some extra steps in order to get this interval, even though we have the function here. We do know that we started from, we're at 100, and then we go to the ground. We started at 2.5 seconds, and then at 5 seconds we hit the ground. So this is the setup for that. This is the f of b minus f of a. This is b minus a. Okay, figure out what that is. Looks like it's -40 feet per second. And negative on velocity just means that it was going downward. Okay, this right here. All right, so you do not have to confirm this algebraically. So don't worry about that. So all of this, just don't worry about it. I have never encountered that in calculus. So I'm just, you know, if it comes up, if you need to learn it in some other time, you can learn it if you're in a more advanced math class. But honestly, I've never used it in calculus. Okay. So what I'm looking for here is symmetry. So is it symmetrical to the x, y, or origin? This guy, I believe, is all three. In fact, 1, 2, yes, he is symmetrical to all three. This guy is just symmetrical to the y. That's all that you need to show. Right here, even or odd. Now this one, I do want you to prove algebraically. Here we plug in a -x. And if it's even or odd, we have to plug in a -x, and we just see what happens. this guy right here actually does become positive. This guy was positive, and he does become negative as a result. This guy is actually odd, which means it's symmetrical to the origin. You don't even need to graph it. You just need, you know that. Okay, and this actually is very helpful when you do integration in calculus. So neither, let's see, negative x, looks like this guy stayed the same. This guy changed. This guy stayed the same. So this guy, because he changed from a positive to a negative, and these guys stayed the same, this guy's a neither. Okay. All right. Last three here for this page, and then we'll do one more. All right, here is the f function, here's the g function, here's the h. This says just take the g, add the f. There's the g plus the f. Can't do much with it. This domain just says that, hey, look, you can't take the square root of a negative number, so therefore we have to make sure that we are larger than -7. Taking the square root of 0 is okay, so that's fine. So just make sure that you do that. So whenever you see a square root, look for the domain restriction. And also, whenever you see division here, square roots and division really break symmetry, so you got to watch out for that. No, square root breaks symmetry. This doesn't. That depends. Maybe I shouldn't have said that. Here's multiplication. Here's the h function times the f function. Blah, 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 blah. No domain restrictions because it's just a cubic. It goes on forever. It's all real numbers, domain and range. This guy right here is the f over the h, but you will notice that there are two values that would give you 0 here. So the two values that would give you 0, okay, if we factored an x out here, we can see that if x was 0, I'd get 0. If x was 5, I would get 0. So these are the two values that you cannot have for the domain. So he would have asymptotes at those two locations, okay? Or at least, no, he would not actually. I think he would have holes. He would have holes there. I don't know. We don't have to graph it though. That's no big deal. Yeah, he would have asymptotes actually. Okay. All right. So let's stop there, and then we'll do one more. All right. So here we've got three functions again. Now here we've got a composition. The f function is going into the h function. So you can see right here, this is the f function going into the h function. So the h function is 3 times something minus 1. Okay, and then we take that f function and put it in it. So this guy goes into the first one. Okay, so kind of keep it. It's like a nest. Okay, the f goes into the h. Here the g is going to go into the f. Okay, the g here goes into the f. So this is what you end up here. And not much to simplify. You did square root so that you can unravel that. But this guy, just leave it as he is. We're good to go. Okay, and because it's a square root, make sure that you do make a little note. It's got to be greater than -7. Looks like h is cubic, and he will be put into a line. Nope, I'm sorry, other way around. The line will get put into a cubic. Okay, and so we end up, is that a cubic or is that squared? Oh, it's squared. Okay, the line gets put into a quadratic. Okay, put that guy in there, blah, 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 ding, ding, ding. And looks like domain is all real numbers. Okay, no problem. It's quadratic. We're good. Okay, it's so weird when my face gets frozen there. What's going on? I don't know why my camera is doing that. Okay, so this is function decomposition. You guys didn't seem to have a problem with that. Yep, make it as simple as possible. And sometimes there's a couple different ways that you could kind of interpret it. You could have put 2x plus 10 as your function here and then just have an x there. That's okay. Okay, here we're evaluating. Okay, we are just plugging those numbers in. I think these guys kind of speak for themselves, so go ahead and pause it right now if you want to double check that work. There's really nothing for me to talk about. Okay, inverse functions, is it 1-to-1? So all you're looking for here is, does it pass the horizontal line test? Okay, if it does, then it is 1-to-1. If it fails the horizontal line test and hits 2 pieces of the function, then it is not 1-to-1. Okay, so this got failed at many locations, and this also fails at many locations. Okay, this guy, even if I drew one here, I'm still missing. There's an asymptote there, so I'm not going to actually hit 2 locations. But everywhere else, I'm hitting 1 location. This guy's 1 to 1. Okay. Okay. All right, these inverses, I love these guys. We got a cubic. Okay. Now this guy's 1 to 1. So I'm sorry, I said cubic. I meant cube root. Cube root is 1 to 1, so he will have an inverse. So just swap out the x and y. Okay, subtract 2. Remember, we're going the opposite order of PEMDAS. Subtract 2. I'll go ahead and uncube root that thing by cubing it, and then add the 7 to the other side. Sweet. This guy is you can see why it's super important. Think of how much work you just, well, maybe not a lot, but you save yourself some work realizing that it fails the horizontal line test, so there's no inverse. Okay, look out for those. Okay, this guy here, he is a quadratic, but it looks like they put a domain restriction, so they only want half of him. Okay, so they kind of saved the day there by saying they want the part that's greater than 0. So go ahead and put it together. You can do that as long as the domain was restricted. They could have done it here by saying that they wanted to be greater than -5. Okay, if they were greater than -5, then you could have actually done it. Oh, I want you to see the punchline. Okay, so we got this guy. We're going to go ahead and swap them. Bop, bop, bop. We're going to move the 7 over there. Then we're going to divide by 4, and then take the square root. You're done. Okay, make sure that you do use that symbol there. That's actually quite important. It's not f to the -1. It would be f inverse. And finally, this guy, this is probably the trickiest of the bunch, just because if you end up with y in 2 different locations here, you're going to have to factor it out. So look out for that. That's probably the hardest out of all of them. If you see 2 x's, both of those x's have to be swapped out, and then you know that you're in for more of a challenging problem, or at least a little something out of the ordinary. Okay? And there it is right there, positive 52. Okay, so these guys are doing double duty here of both graphing and of showing that they are actually inverses. So we go ahead and show that G is an inverse of F, and then technically you have to show that F is an inverse of G. Okay, so this is what you want to do, and you should get X at the end of the rainbow, and these guys should look symmetrical on the Y equals X. Okay. So here, this guy was we're staying at 0, but we're going to drop 2. So it looks like this guy is right here. So that would have been this guy. So this guy's F. Oops. F. So F is these 2. And then G is this guy and this guy. Okay. So you can see when you graph them, that they should be they have this nice symmetry off of each other. Okay, if that doesn't happen, you know something's up. Okay, same here, last one. The crown jewel of the study guide. This is putting 1 into each other, and just be careful. And in one step, things should start unraveling. Like right there is 2. Those cancel out right there. The cubed root gets cubed. That cancels out right there. Okay, it's perfect. It's beautiful. Also, this right here, those guys cancel out to 0. This cubed root of something cubed undoes it. 2 times that, bam. It's really, they should just flow everything should flow nice and simple when you're trying to find those inverses. Okay, or prove their inverses. Okay, that is it. Good luck, everybody.